So, in the last class we have started the transportation problems. We are trying to find out the initial basic feasible solution by different methods like northwest corner rule, row minimum, matrix minimum and the least square method and the least matrix method. We will do the last one today, that is the VAM, that is Vogel's approximation method. Let us see what the VAM says. The VAM is an improved version of the least cost matrix method, least cost matrix minima method, but it may not always produce the better BFS, that is basic feasible solution. It not only considers the least cost Cij, but also the costs which exceed Cij. What are the steps? Step 1 is, for each row you determine a penalty cost by subtracting the smallest unit cost element in the row or column from the next smallest unit cost element in the same row. That is what happens. You consider a row. In one row what happens? You have the costs are there. You find out the least and second least cost, and what is the subtraction value. If you subtract these two, what is the value you are writing for each row. Similarly, for each column what you are doing? You are finding out the least cost and the second least cost, and you are writing the difference of these two. So, this is the step 1, that for each row, for each column find the lowest and the second lowest cost, and the difference of them you write in one form which we call as ui and vj. Afterwards, you will see. In step 2, identify the row or column with maximum penalty if ties occurs break arbitrarily. That is, you identify a row, you have the differences of the cost for each row, for each column, you identify the row which has the maximum penalty. If maximum penalty occurs in more than one row or column, arbitrarily you can choose any one of them. Then allocate as much as possible with the least unit cost in the selected row or column. As we are allocating the available depending upon the availability or demand, you allocate as much as possible on the selected row or column. It may happen that the row or column is availability or demand is not fully satisfied, then on the second one, on the second other cell also you can go on the same row or the same column. If a row or column is satisfied simultaneously, then only one column will be used. That is, one row, or if a row or column is satisfied simultaneously, only one of the two is crossed out and the remaining row or column will be assigned the 0 supply or 0 demand. So, therefore, if a row or column is satisfied simultaneously, only one of the two is crossed out, that is, you cross out whichever you have already satisfied, and the remaining row or column will be automatically assigned 0 supply or demand depending upon the availability. Now, come to the step 3. In step 3, if exactly one row or column with 0 supply or demand remains uncrossed out, only one row or column with 0 supply or demand remains uncrossed out, then stop. That means, you have allocated all the cells depending upon the availability and depending upon the requirement. So, you can stop. B is, if one row or column with positive supply or demand remains uncrossed out, then determine the basic variables in the row or column by least cost method and then stop. That means, if it is one row or column with positive supply demand remains uncrossed out, then you use the least cost method whatever we discussed in the last class. Number C is, if all the uncrossed out rows and columns have 0 supply and demand, then determine the 0 basic variable again by the least cost method and then stop. Otherwise, go to step 1 and repeat the process. So, if you see here what is happening, we are finding out the penalty between the least cost and the second lowest cost between of the rows and the columns. You are finding out the maximum of the maximum penalty you are allocating on that row or column, and then you are, if required, you are crossing out and then you are repeating the process. Let us take one example for this one. Let us verify this one. You have one matrix on the same example, actually whatever we did for the last class. that is I am having 3 rows and I am having 4 columns, that is 1, 2, 3 and 4 columns. Costs are 21, 17 and 32. Here it is 16, 18 and 27. Then we are having 25, 14 and 18. We are having 13, 23 and 41. The availabilities are 11, 13 and 19, whereas here it is 6, 10, 12 and 15. So, what I have to do using VAM method? The VAM method, first I have to find out for one row what is the least cost and what is the second least cost. If you see in the first row, least cost is 13 and the second least cost is 16. So, difference of 16 minus 13 is 3. So, within bracket I am writing here. Similarly, for the second row, if you see the least cost 14, second least is 18, difference is 4. For the third one, it is second least is 17. So, this also will be 3. The least is 14, second least is 17, not 18. So, it will be 3. For the third row, it is 18 and the second lowest is 27. So, difference is 9. Similarly, for each one, each column also you find out the penalty or the difference. Here it is 17 minus 21. So, it is 4. Next one is 16 minus 18. So, it is 2. Next one is 14 minus 18. So, it is 4 and then you are having 15, 13 minus 23, that is 10. So, if you see the maximum penalty occurs on the fourth column, which value is 10. So, in this case what you will do? Now, you have to allocate over here, since 10 is the fourth column is the maximum penalty occurs. In the fourth column, you now find out what is the least cost cell. The least cost cell is 13. Availability is 15, demand is availability is 11, demand is 15. So, therefore, the minimum of these two is 11. So, you can allocate 11 over here. Once you are allocating 11 over here, so this becomes now availability becomes 0 and this becomes 4. So, already 4 demand 4 you can allocate in this particular fourth column. Now, remaining two cells 23 is the lowest, where the demand is 4 and the availability is 13. So, you can allocate this 4 over here. So, basically now it becomes 9, this 4 becomes 0. So, at the end of first step, after calculating the penalties, your maximum penalty was on column 4. So, you have allocated first on the lowest cell was 13, the minimum of 11 and 15, that is 11. The remaining demand 4 you are meeting on the next lowest cost cell, that is on this cell 2 4, you are allocating 4 units. So, now since the entire demand has been fulfilled for the column 4, in the next iteration you can delete column 4 as well as the availability of the first row is exhausted, availability of the first row is also 0. So, in the next step you can delete the first row and the fourth column. So, you will get actually a matrix with 2 rows and 3 columns only. The data will be 17, 18 and 14, next one is 32, 27 and 18. What is the availability? Availability for the second row was 9, for the third one is 19 and here it is 6, 10 and 12. Now, repeat the same process from the beginning, that is again you find out the minimum of the lowest cost and second lowest cost for the rows and the columns respectively. So, I am not repeating, I am just writing the result 14 minus 17 3, then 18 minus 27, this is equals 9, here it is 15, here it will be 9 and here it is 4. So, your maximum penalty occurs on the column 1, that is 15. So, on column 1 the lowest value is 17. Here if you see demand is 6, whereas the availability is 9. So, maximum you can allocate which is 6. So, now what happens? You have allocated 6 over here. Now, the demand is 0. So, on this column you cannot allocate any other thing on any other cell. So, in the next step what you will do? You can delete the column 1. So, now you are having only 2 rows and 2 columns. So, the values are 18 and 14 and 27 and 18. Here you are having 6 already you have allocated. So, it has become 3. So, it is 3, this is 19 and here it is 0. So, it is 10 and 12. Now, repeat the process 4, 9, here also it will be 9 and 4. You can allocate any one of you can, if you wish, you can allocate any one of these two, any one of these. So, let us take this one, this row, second row, 9 is there, arbitrarily you can choose. So, in this your lowest value is 18 and demand is 12, whereas availability is 19. So, 12 you can allocate over here. So, once you are allocating 12, this becomes 0. So, on this row again you can allocate something more, because 19 is the available, demand is 10 for this second row and first column. So, you can allocate 7 over here. So, that now this becomes basically 0, you have allocated this and this has become 3. So, now if you see, you can delete this first column and this is also not necessary. So, there will be only one column over here, sorry, one cell will be here where availability is 3 you are and the demand is 3. So, basically after this you are deleting this column, this row and this column. So, only demand and availability is 3, only one column. So, your result is 3. So, you see you have allocated like this, one is this one, another is this, here this, then these two and this one. So, the solution I can write down x 14 is equals to 11, x 21 I am just writing in order, x 21 6, x 22 is 3, x 24 this is equals 4, x 32 this is equals 7, x 33 this is equals 12. And if you calculate the cost will be 796. If you compare with the other matrix minima method, that was 812 or something. So, at least for this example using the VAM approach, you are obtaining the least cost for the VAM method for this problem, but it is not guaranteed that always you can obtain the solution like this. Now, come to the, I hope the procedure to find the initial basic feasible solution using these methods is clear to you. You can use any one of these methods to obtain the initial basic feasible solution, and the next step is how to find out the optimal solution from the initial basic feasible solution. We have to find out this thing. So, let us see the other part, that is the optimal solution now of LP transportation problem. For the optimal solution, what I have to do? Now, you have the, if you remember, you have m cross n transportation problem, that is you are having m cross n decision variables as well as m plus n constraints are there. Now, two things can happen. The basic feasible solution, initial basic feasible solution, whatever you have obtained, that is degenerate or that may be non-degenerate. Now, the initial basic feasible solution will be non-degenerate if in the initial basic feasible solution we have made exactly m plus n minus 1 allocations. Please note this one, if we have made exactly m plus n minus 1 allocations. So, this is first one, your initial basic feasible solution will be non-degenerate if we have made exactly m plus n minus 1 allocations in the initial basic feasible solution. And number 2, whatever allocations we have made, these allocations we have made, this allocation does not form a loop. this allocation does not form a loop. Form a loop means what? You are starting from one cell, you are visiting different cells and you are coming back to that particular cell, that we call it as the loop. So, for non-degenerate solution we have two criteria. One is the initial basic feasible solution should have exactly m plus n minus 1 allocations, and this allocation does not form a loop. Let me take one example. Let me take one 3 by 4 matrix, something like this, 3 by 4 matrix here. This corresponds to the cell 3 1, as you know. From here I am moving to cell 2 1 say. From cell 3 1 I am moving to the cell 2 1. From cell 2 1 I am moving to the cell 2 2, and then from cell 2 2 I am moving to the cell 1 2 like this. From 1 2 I am moving to the cell say 1 3, this is your 1 3, cell number 1 3. From cell 1 3 you are coming back to cell number 3 4, and from 3 4 if you can go back to the original cell, that is 3 1. So, this forms a loop. So, you are having a cell 3 1, from 3 1 you are visiting to 2 1, from 2 1 you are visiting to the cell 2 2, from 2 2 you are visiting the cell 1 2, from 1 2 you are going to 1 4, from 1 4 you are coming to 3 4, and from 3 4 you are going back to the original one. So, this kind of loop should not be there, then we call it as the non-degenerate solution. And if these criteria are not satisfied, in that case we say that the solution is degenerate and we have to handle it separately, that we will see afterwards. So, please note that in a loop always we will have even number of cells. If you see the figure, always we will have in a loop only even number of cells. Loop can be formed by even number of cells only, and the shape of the loop may or may not be square type. It may be of square type, it may not be of square type. And each cell you are basically doing one plus and one minus, that is you are moving, whenever you are moving you can move either one cell up, down or left or right. You cannot cross more than this one. Now, two theorems are available on this. If you see this one, theorem 1, it states that here let X be a set of column vectors of the coefficient matrix of a transportation problem. So, and then a necessary and sufficient conditions for the vectors in X to be linearly dependent is that the set of corresponding cells will form a loop. So, if the set of vectors X are linearly dependent, they will form a loop, and from theorem 1 it is very clear, if the set is linearly dependent, then it cannot be the optimal solution, and that is clear again from the theorem 2. If you see, a feasible solution to a transportation problem is basis. A feasible solution to a transportation problem is basis if and only if corresponding cells in the transportation problem do not form a loop. So, the feasible solution or the allocations whatever you have made to the transportation problem, that will form one loop, that if that will be the basis, that will form a basis if there is no loop. So, for this reason we are telling, if there is a loop, then degeneracy will occur and we will see how to handle it. The next step is the transportation algorithm. The solution procedure of a transportation problem is a special case of simplex method. As I told yesterday, transportation problem is a special case of simplex method, a linear programming problem. Here what we are doing, in step 1 we are determining the initial basic feasible solution. Then we are checking the, in step 2 we are checking the optimality condition to choose the entering variable among non-basic variables. Just we have done it for the case of simplex algorithm. From the initial basic feasible solution, if that is not the optimal solution, there must have some entering variable among the non-basic variables. So, after checking the optimality condition, we are finding out what should be the entering variable among the non basic variables. If the optimality condition has been satisfied, then you stop, otherwise you go to step 3. In step 3, again using feasibility condition, we have to find the leaving or departing vector from the current basis, whatever we have done for the simplex algorithm. So, you have to find out the new basic solution and then go to the step 2, that is again check the optimality and repeat the process whatever we have done earlier. Now, how to choose the entering variable or the departing variable? Easiest way is, I am just writing, I will explain it with one example, sorry, with algorithm. You have the problem, this one, summation minimize z equals summation I equals 1 to m, summation j equals 1 to n, c I j x I j. You are subject to a I minus summation j equals 1 to n, x I j equals 0, I equals 1, 2 and like this m, and your b j minus summation I equals 1 to m, x I j, this also should be equals to 0. This we have discussed, j will be 1 to n, and x I j greater than equals 0 for all I and j, for all I and j. So, if you see, this transportation problem is basically one is having m cross n variables and m plus n constraints. If you think that I want to solve it using the dual method, then the dual of this problem will have the just the opposite one, that is m plus n variables and m into n constraints. So, whenever you are having m into n constraints, so if you use the dual variables like u 1, u 2, u m and v 1, v 2, v n, v 1, v 2, v n, in that case your condition or the constraint would be something like this: u I plus v j should be less than equals c I j. u I is the corresponding variable and v I is the variable for this, for the second constant. So, c I j, where your I varies from 1 to m and j varies from 1 to n. And obviously, u I and v j are unrestricted in sign, they may take any value. Now, we can show this thing, I am not writing this, z I j minus c I j, z is the objective function value, c I j is the coefficient. We can show it that z I j minus c I j is u I plus v j minus c I j. And for basic variable, what should happen? Your z I j minus c I j should be equals to 0, or for a particular value of I and j, say for I equals r and j equals s, this condition should be always satisfied. U r plus V s equals C of R s, U r plus V s equals C of R s. If for the if all z I j minus c I j less than equals 0, in that case optimal solution has been achieved, otherwise optimal solution has not achieved, or in other sense, if z I j minus c I j is greater than 0, optimal solution has not been achieved, and we have to select the entering vector and we have to select the departing vector. Of course, if you write it in the other way round, c r s minus u r plus b s, then it will be the opposite one. So, basically you see, you have to calculate c I j minus u r plus v s. So, c I j is the coefficient of a particular cell and u I and v j already we have calculated using the VAM approach. If you see, we have calculated. Let me explain it by the flow chart. You see the flow chart over here now. Let us start from the original problem. Express the problem in the tabular form, that is in the tabular form means whatever form already you have seen. Is it a balanced problem? You know the balanced problem means total availability and total demand should be equal. If it is not a balanced problem, then we can add the balanced problem, we can make it a balanced problem, and by adding the dummy row or the dummy column to it, and then basically from here I should come to the next one, that is find the initial solution. then is it the maximization problem? If yes, then convert it into a minimization problem and go to the next step. Otherwise, you find the initial basic feasible solution using northwest corner rule, the list matrix method, VAM method, etc. Whatever method you want, you can use. So, basically first you are checking whether the problem is balanced or not. If it is not balanced, using dummy row or dummy column, you convert it into a balanced problem. We will see just by one example how it can be converted into the corresponding balanced problem. The next one is it degenerate? As I told you, for non-degeneracy there should have exactly m plus n minus 1 allocations in the initial basic feasible solution, and there should not be any loop. So, if it is degenerate, then we are telling remove degeneracy by assigning a very small quantity epsilon to the requisite number of cells. Again, I am not explaining this one at present, I will explain it through some example. If it is not degenerate, in that case you see, using the cost coefficients of the occupied cells, compute the index value for row I, u I equals C I j minus B j, and for column j, B j minus C I j minus u I, and then assign an arbitrary index value, say 0 to the first row or the row which is having the highest number of allocations on the right margin. Actually, from this it is not clear to you, I can understand. We have told you C I j should be equals to u I plus V j. So, at first you have to calculate what is your u I, what is your V j from the example, and how to calculate what is the value of u I and what is the value of V j, that we will show you. Please note that u I and V j will be calculated from the cells which has been allocated only from the initial basic feasible solution. We can find out u I plus V j by writing a set of linear equations, and then as we have told, if you see the index value you are writing as 0. So, some variable of this u I and V j, one of them you have to make as 0, and then calculate the values of u I and V j. Once you have calculated the value of u I and V j, your next step is compute the opportunity cost for each occupied cell. Please note this one. Compute the opportunity cost for each occupied cell by using the formula delta I j equals C I j minus u I plus V j. So, you are, once I know u I and V j, I can calculate delta I j equals C I j minus u I plus V j, but delta I j will be calculated only for the allocated cells or the occupied cells. If all the delta I j greater than 0, if it is yes, the solution is optimal. If you remember, I told Z I j minus C I j should be less than equals 0, then we are getting the optimality. Here C I j minus u I plus V j we have done. For this reason, we are telling delta I j should be greater than equals 0, then the solution is optimal. If the solution is not optimal, that is, if all delta I j is not greater than equals 0, then select the cell with smallest opportunity cost, that is the smallest cost, then draw a closed loop which begins and ends with at the cell selected. That is, you are selecting a cell, you are forming a loop, and then it may pass over both occupied and unoccupied cell. That means, whenever you are drawing the loop may pass through both occupied and unoccupied cells. Then has the alternate sign in the root starting with plus sign and the chosen cell. That is, whenever you are starting with this, in one case you will have plus sign, then on the same row or column you will have the minus sign. This we are doing to balance the allocation or to balance the demand. Then change the direction only at the occupied cells. Please note this one. You can change the direction of a cell, that means you are moving in one side, you want to move to the right side, you can move on the right side only from a occupied cell only. From non-occupied cell you cannot move this one. So, this is the algorithm for choosing or for finding the optimal solution. So, let us see now how we can do it. Let us take the example 3 cross 4 matrix. So, we are having 3 rows and 4 columns. Cell entries are like this, column wise 1 3 4, next column 2 3 2, this is third column 1 2 5, fourth column is 4 1 and 9, the costs. So, you have the origins O1 O2 O3, say this is O1 O2 O3 origin, these are the destinations D1 D2 D3 and D4. The availabilities are 30, 50 and 20, and on this side the demands are 20, 40, 30 and 10. If you see, the sum of the availability is 100, 30 plus 50 plus 20, whereas the sum of the demands are 20 plus 40 plus 30 plus 10, which is also 100. So, therefore, this is also the 100. So, total demand is equals to total availability. So, the problem is a balanced transportation problem. So, using the different kind of methods like VAM or other methods, as we have discussed earlier, we can find out the initial basic feasible solution. I am not discussing that one at present. So, I am writing what is the initial basic feasible solution of this problem. So, this was the problem, then if you wish you will get this thing 20, 20 and then you are having say 10 over here, here 20. So, this table shows that x 11 your initial basic feasible solution is x 11 20, x 13 this is equals 10, x 22 this is equals 20, x 23 this is equals 20, x 24 this is 10 and x 32 equals 20. So, this is the initial basic feasible solution. The methods we discussed earlier, from that directly you can write down. So, therefore, here you see 20 plus 10 30, 20 20 10 50, 20 column wise also it is matching. Now, what is the number of allocations here? Number of allocations are 20, 1, 2, 3, 4, 5, 6. And what is m plus n minus 1? M plus n minus 1, this is equals m is 3, n is 4 minus 1, which is also 6. So, number of allocations equals m plus n minus 1. So, this is non-degenerate problem, this is not a degenerate problem. So, now what I have to do? I have to calculate Cij equals ui plus Vj, ui plus Vj for all the occupied cells. Please note that Cij equals ui plus Vj for all the occupied cells only. So, what is happening? For the first cell 1 1 this is occupied. So, I is 1, j is 1. So, what equation you are getting? E1 plus V1 this is equal C11, C11 is how much? Value of C11 is 1. So, first equation is E1 plus V1 this is equals 1. The next one is 1 3, that is this cell, the cell 1 comma 3. So, here I is 1 and j is 3. So, therefore, U1 plus V3 this is equals again the C13 the cost is 1. So, U1 plus V3 equals 1. The next occupied cell is 2 2. So, therefore, U2 plus V2 that is equals the cost C2 2 3. Next occupied cell is 2 3. So, therefore, U2 plus V3 this is equals 2. The next occupied cell is 2 4. So, similarly, you will get U2 plus V4 that is equals cost here is 1. So, U2 plus V4 equals 1. Next and the last occupied cell is 3 2. Therefore, U3 plus V2 sorry this is U, let me write clearly, U3 plus V2 that is equals 2, because the cost is 2. Now, arbitrarily you can choose any one, but it is better in by convention the row or column which is having maximum number of allocated cells, you choose that corresponding variable equals to 0. Just like here, if you see row 2 has maximum number of allocations, that is 3. No other cell is having, no other row or column is having 3 number of occupied cells. So, I can make u 2 equals 0. So, we are choosing this one, you are choosing, note this one, you have to choose, otherwise you cannot obtain the values of others. You are choosing u 2 equals 0. So, once I have obtained u 2 equals 0, now you see from here you can obtain the other things u 2. So, V 2 will be equals to, from this equation, since u 2 is 0, your V 2 will be, from this equation V 2 will be equals to 3, then V 4 is equals to, V 3 is equals to 2. From the next equation V 3 equals, from this equation u 2 is 0. So, V 3 is 2, again from this equation your V 4 is equals to 1. Once you have obtained V 4, then you have to find out u 1, already I know u 1, your what is your u 1 plus V 1, V 1 is not known till now, V 4 you have done. So, what is V 1? V 1 is, sorry, u 1 plus V 3, from here I can find out what is u 1, u 1 plus V 3, V 3 is 3. So, this one will be equals to V 3 is 2. So, this will be u 1 will be minus 1, V 3 is 2. So, u 1 is equals to minus 1. So, once u 1 is minus 1, you can find out what is V 1. V 1 is u 1 plus V 1 is 1. So, therefore, your V 1 is u 1 is minus 1. So, your V 1 will be, from where V 1 I can obtain, from here only I can obtain V 1. So, minus 1 1. So, this will be V 1 will be 3, and u 3 you can find out from here, u 3 will be equals to, from the u 1 u 2 u 3 plus V 2 equals to, V 2 is known 3. So, u 3 will be minus 1. So, once I have, like this way you can obtain the values of these variables. So, I think the method is clear to you. Please check this thing once more, please check once more, that is what you are doing. You have the formula Cij equals Ui plus Vj. Once I am getting Ci equals Uij plus Vj. So, therefore, for the occupied cells only you have to write down the equation. For the first occupied cell is 1 1, you are writing u 1 plus V 1 equals C 1 1, whose value is 1. Similarly, for the next occupied cell is 1 3. So, u 1 plus V 3, I is 1, V is 3. So, j is 3. So, u 1 plus V 3 equals corresponding cost 1. Next occupied cell is 2 2. So, you are writing u 2 plus V 2, this is equals 3, and you are going on like this way. Then you have to choose arbitrarily one of the value of ui or Vj as 0. How to choose it? The convention is that you choose, you see the row or column which has maximum number of allocations. So, the row or column which is having maximum number of allocations, the corresponding ui or corresponding Vj, you make it as 0. So, once I have done this one, for this particular problem, if you see over here, in this particular problem, the second row is having maximum number of allocations, that is second row corresponds to the variable u 2. So, I am making u 2 equals 0. Once I am making u 2 equals 0, by substituting the values of u 2 in other equations, you can obtain the different values from here. So, once I have obtained the different values, now rewrite this table, and also write down corresponding ui plus Vj. So, let me write down this table once more. Let me rewrite it. I am having 3 columns, 3 rows and 4 columns. So, 1, 2, 3 and 4. The values are 1, 3, 4, column wise I am writing 2, 3, 2, this is the repetition 1, 2, 5, 4, 1 and 9. Allocations are 20 here, 10 here, then 20, 20 and 10 over here and 20 is coming here. I am not writing now the total demand or total availability. Instead of that, I am writing UI and Vj. Values are whatever was calculated from there. So, calculated values are 0, 3, 2 and 1. Now, what I have to do? I have to compute this one, delta ij equals Cij minus ui plus Vj, and I will calculate it for which cells? I will calculate it for unoccupied cells. Please note this one. I will calculate it for unoccupied cells. It is very easy to calculate. First cell is occupied, second cell is not occupied. So, basically it will be 2 minus 3 minus 1 for this cell 1 2. For the cell 1 2, what happens? It will be 2 minus 2 is C I j minus u I plus B j, that means minus 1 plus 3. So, this is 0. So, like this way u I plus B j C I j minus u I plus B j for the unoccupied cells, and I am writing it within a circle. So, basically delta I j, this value I am calculating for the unoccupied cells, and within circle I am writing what is the value. So, similarly for this one, next one, C I j minus u I plus B j. So, this is 0. So, the value will be 4. Mechanism is clear, I think. For the next one, C I j minus u I plus B j, u I B j both are 0. So, here it will come as 3. The next one is 4 minus 0 minus 1. So, 4 plus 1, this will be 5. Then for the next one, 5 minus 1, so it will be 4, and for the last one 9, it will come as 9. So, if you see here, the delta I j for unoccupied cells all are greater than equals to 0. So, what we have told? If delta I j is greater than equals 0, then the solution is the initial basic feasible solution. Whatever we have obtained, this solution is the optimal solution. So, therefore, your solution you can write down x 11 20, x 13 is 10, x 22 is 20, x 23 equals 20, x 24 equals 10, and your x 32 this is equals 20, and optimum cost or Z star, if you say, this will become 180. So, therefore, whenever from this we have shown, if you have the initial basic feasible solution, just from here you have the initial basic feasible solutions, you are checking it is not degenerate, because number of occupied cells equals to m plus n minus 1, then you are calculating C I j plus u I plus B j for the occupied cells, you are getting some equations. From these equations, you are setting one of the variable equals 0, for which that row or column has maximum number of allocations. Once I am setting one variable as 0, from here you can find out the values of the other variables. Once I have obtained the values of the other variables, then in the next step is you rewrite the table in this particular format, you calculate u I, you calculate V j, then you calculate delta I j equals C I j minus u I plus V j, delta I j equals u I C I j minus u I plus V j. So, just like 2 minus 1 plus 3 u I plus V j, and that value is 0. Like this way, for all unoccupied cells you are calculating the delta I j. If delta I j is greater than equals 0, you will stop, and this is the optimal solution. So, optimal solution exists. So, this is one case. Now, let us see the second case, that whenever you are having the degeneracy, whenever if delta I j is not all delta I j not greater than equals 0, how to handle the situation? Sorry. No. Let me make 4 rows and 3 columns only. 1, 2, 3, 4, 1, 2 and 3 columns. Row wise the values are 2, 7, 4, 3, 3 and 1, 5, 4 and 7, 1, 6 and 2. The availabilities are 5, 8, 7 and 14. Here you will get 7, 9 and 18. So, I can find out the initial basic feasible solution for this case. The initial basic feasible solution again I am not showing to you, directly I am writing because already we have done this thing. So, the allocations are something like this. One is 5 over here, the next one will come as 8 over here, then on the cell 3 to 7 will come, and here it is 2, 2 and 14. So, this is 5. So, it is matching with the availability, then on 2 3 it is 8, then on 3 2 7, then it is 4 1 2, 4 2 2, 4 3 14. So, it is matching with the all availability and the demand. This is 34, this is 5 8 13 20 34. So, total demand equals total availability. So, therefore, it is balanced problem. Number of occupied cells is equals to 1 2 3 4 5 6 and m plus n minus 1 is also 3 plus 4 minus 1, that is 6. So, it is non-degenerate problem. Now, next what you have to do? You have to calculate now what would be the Cij equals Ui plus Vj for the occupied cells. So, Cij equals Ui plus Vj, that is for the first one. I am just writing the equations of this. The equations will be, for the first case it will be U1 plus V1, this is equals, the cost is 2. Next the cell is 2 3. So, that you will have U2 plus V3, this is equals, cost is equals to 1. Then 3 2, the cell is 3 2 is occupied, that means U3 plus V2, that is equals, cost is 4. Then 4 1, so U4 plus V1, this is equals, cost is equals to 1. Next one is U4 plus V2, U4 plus V2, this is equals 6, and the last one is U4 plus V3, this is equals 2. So, row 4 has maximum number of occupied cells. So, you can set U4 equals 0. Once you have set U4 equals 0, then now you can find out, I think, what are the values of U1, U2, U3, U4 is already known, and V1, V2, V3. If you calculate, you will obtain U1 is equals to 1, U2 minus 1, U3 minus 2 you will get by solving these equations only. V1 equals 1, V2 equals 6 and V3 this is equals 2. So, once I obtain this one, I have to formulate the next table from here, that is I have to reproduce the table. The table is, I am having 4 rows and 3 columns. So, 1, 2, 3, 4 and I am having 3 columns. You are having 2, 7, 4, 3, 3, 1, 5, 4, 7, 5, 4 and 7, 1, 6 and 2. Costs are given 5, 8, 7, 14, 5, 8, 7 and 14, and here it is 7, 9 and 18. Now, you write down u I and V j. Already we have calculated u I, that is 1, -1, -2 and 0. You calculate V j values are 1, 6 and 2. The occupied cells are this one 5, then here it is 8, here it is 7, then it is 2, it is 2 and this is 14. So, now calculate delta I j equals u I minus V j, as I have told in the C I j minus u I plus V j. You calculate this thing, delta I j equals C I minus this one, the cell 1 2 is unoccupied, cell 1 2 means it is u I plus V j is 7. So, C I j minus u I plus V j is equals to 0. So, I think for the next one, again 4 minus 2 plus 1, that is equals to 1. I am showing for this, next example I will not show. I will directly write down, this is 3 minus 1 minus 1. So, this will be remaining 3. This is 3 minus 6 minus 1. So, it is becoming minus 2. The next one is 5 minus 1 minus 2. 5 minus 1 minus 2. So, it will become 6. On the same way, if you write down, this will be 7. So, you calculated delta I j. Here if you see, all delta I j is not equals to 0. All delta I j is not equals to 0, delta 2 2, this is equals to minus 2. So, delta 2 2 is minus 2, which is less than 0. So, now you have to form a loop. You have this one. Associated with this, if you see, you are having, this is an occupied cell, this is an occupied cell, this is an occupied cell. So, if I traverse something like this way from here to here, or from here to here, from here to here, from here to here and from here to here, something like this. In that case, what will happen? In that case, I will traversing this and the least cost is 2 here. So, what I will do in this cell, now I will add to 2 allocation, I will allocate 2 in this cell and accordingly these cells I have to adjust. Or in other sense, other way you can tell that you are allocating 2 over here, the least, please see here what was the allocations. From the allocations you are taking the least cell. So, if I draw the table only for this one, you are having the 4 cells, 4 rows and 1, 2 and 3. I am not writing all others, I am just writing 8 is here, you are having your 14 is here, you are having your occupied cell was 2 over here and this is not occupied. So, what I have to do? I have to move from here, I have to allocate 2 over here. Once you are moving like this, to adjust I have to allocation, I have to reduce by 2. Then I am coming here, so I am moving in this direction. Here, since on this column I have made 2 less allocations. So, here also that was 10 or 14, whatever it may be, sorry, this allocation will be 10, not 14. 2 plus 2 plus 10. So, this allocation will be 14. So, once I am making this allocation as 14, therefore, this is 10. So, this allocation now will become 10 plus 2 and once you have made 2 more allocations. So, you are going to this side, then here you have to make 2 less allocation, that is 2 minus 2. So, now this cell will not be occupied and from here when you are moving automatically you have added 2. So, like this way you are forming the loop. From this table you are finding out, you will form a loop using these cells. Among these, among the occupied cells, what is the minimum allocation? That minimum allocation you are adding to this negative cell and then you repeat the process. So, once I have done this, my new allocation will look something like this. I am having 4 tables, 1, 2, 3 and 4 and I am having 1, 2 and 3 tables. So, it is 2, 7, 4, you are having 3, 3, 1, you are having 5, 4 and 7, 1, 6 and 2. Now, the allocations are you are here you are having 5, then you are allocated 2 here, the new allocation whatever you have done that you have made here. So, this allocation has been reduced to now 6, this 7 is untouched, this one 10 was there, you have allocated 2, and now if you see these 2 allocation over here. So, after this the new allocation is this. So, once I have made new allocations for the occupied cells, again you have to calculate C I j plus U I plus V j, and you have to tell what are the values of U I and V j. I am directly writing the values of U I plus V j 1, -1, 0 and 0, and V j will be 1, 4 and 2. So, once I obtain this one for unoccupied cells, now you calculate delta I j equals C I j minus U I plus V j. You can calculate it and check it afterwards. So, it becomes 2, 1, this is 3, then this one will become 4, this one will become 5 and this one will be 2. So, all delta I j is greater than equals 0. Since all delta I j is greater than equals 0, therefore, we obtain the minimum optimal solution over here. The optimal solution can be written as x 11 equals 5, x 22 equals 2, x 23 equals 6, x 32 equals 7, x 41 this is equals 2, x 43 this is equals 12, and the minimum cost, if you calculate, the minimum cost will now become 76. So, 2 more cases left over, one is if degeneracy occurs and one is the if you have the unbalanced problem. So, in the next class what we will do? We will just complete these 2, that is what happens if we have degenerate transportation problem and if I have unbalanced transportation problem, and then we will go to the next problem, that is the assignment problem. Thank you.